that we take for the problem after we factor. And we'll do a couple little examples so you can see what I mean. So the first thing we did was just simplify fractions, right? Like I gave you a single fraction and we just had to simplify it. So simplify. And an example of that would be if I just gave you like, say like 4x minus 8 over x squared minus 4. So what do we factor when we're just simplifying? Do we factor both the numerator and denominator or just the denominator? What? Yeah, we do both, right? Because the only thing we have to do when we're simplifying is just like cross stuff off. But both the numerator and denominator have to be fully factored in order to do that. And really all of the problems that we do, other than solving equations, like get back to this point at some point, you know, like after you add two fractions, you have a single fraction and then you have to simplify it. So this is sort of our goal, is to get to the point where we have a single fraction and we can completely factor both the numerator and denominator to simplify it. So we're going to do both. And then we're just going to cancel common factors. Maybe if I can write, there we go. So in this example, we would start by factoring. We have a GCF of 4 on top, and then the difference of squares on the bottom. So we factored both the numerator and denominator, and then we identify any common factors and cancel them. So we would get 4 over x plus 2. And in that final answer, you don't necessarily need the parentheses around the x plus 2 because there's nothing else going on in the denominator, but I would always rather have them and not need them than need them and not have them. So if you want to leave them, that's totally fine. So then the second thing we did was we multiplied. So that might look something like x over x squared minus 25 times x plus 5 over x squared. And this, remember, was essentially the same exact thing as simplifying. We just like smush the two fractions together and then factor everything and cancel. So again, we want to factor both. Sorry, this is lagging. There we go. Both numerator and denominator of both fractions. And then again, just cancel common factors. So these are essentially the same thing. So here, remember, if there's addition or subtraction, we put it in parentheses, like so. And then x and x plus 5 cannot be factored. X squared minus 25 is x plus 5 times x minus 5. And then x squared is a monomial factor, so there's no addition or subtraction, which means I can do prime factorization and just call it x times x. So that's one of the subtleties to notice is like I didn't write this x squared as x times x because it was being added or subtracted with another term in the denominator, which meant I had to factor that entire x squared minus 25. I couldn't just do like x times x and 5 times 5. Whereas this x squared doesn't have any addition or subtraction happening in that denominator with it, and so it's a single factor. I can factor it just using prime factorization. So that's why we use those parentheses, because they tell us I'm factoring this whole thing as opposed to like just this one term. So then we would cancel some common factors, and this ends up being 1 over x minus 5. Or sorry, 1 over x times x minus 5. Yeah, I'm sorry, I wrote it and didn't say it. There we go. And then the next thing we talked about was division, right? And division was essentially the same. We just had to write it as a multiplication problem. So our approach for division, so that would be something like, I mean, I could just take the same exact two fractions. It's not going to be very exciting, but... If I wanted to divide those two fractions, well, I still factor numerators and denominators. But then before I can cancel anything, I have to rewrite it as multiplication. We're going to cancel that. And then cancel common factors, right? So we rewrite it as multiplication by taking the reciprocal of the divisor. So over here, again, I've got parentheses here and here. So we have x over x plus 5 times x minus 5. And then our factorizations are the same as they were in the last problem, but this is going to be the reciprocal. And then we can write that x squared again as x times x, although it doesn't do us any good in this case. Like, we just don't end up with any common factors, right? Because I only have binomial factors in the denominator, and I only have monomial factors in the numerator. You can't cancel. You can never cancel a polynomial with a different number of terms. So, I mean, like I said, this one doesn't turn out super interesting. But if we wanted to be fancy and write it with exponents, it would look like that. So there doesn't end up being anything that cancels in that particular case. Okay, so one key difference between these three and like addition, subtraction, is that when you do simplify, well, I mean, simplifying, you only have one fraction, but when you do multiplication and division, like, you don't need common denominators ever. That's probably one of the most common mistakes that we see on this test, is on the multiplication problems, people try to get common denominators, and it just gets really, really messy. And then people just kind of get lost. I mean, it's overwhelming if you try to do it with a multiplication problem, because you just end up with so many factors. So remember, on these ones, you don't get common denominators. So that's one of the key things you want to remember as far as the difference between sort of your multiplication division problems and your addition subtraction problems. Let me just copy this. Okay, so continuing on, I can't fit it all on one page, but let me do it this way. Okay, so next we're going to think about addition and subtraction. So when we do addition and subtraction, our first goal is to get common denominators. And so since our initial approach has nothing to do with the numerator, it just has to do with getting common denominators, that's the only thing we factor. So we only factor the denominators here. And then the approach we're going to take is that we want to get common denominators. So we want to make all the denominators the same. What we can't do here is clear fractions because there's no equal sign, so we don't have two sides of the equation to balance out like that multiplication, right? If you think about like 1/3 plus like 4/3, that definitely has a very different value than 1 plus 4, right? And if we had an equal sign and something on the other side, we could multiply both sides by 3 so that we change the value of both sides in the same way. But if we multiply just this expression by 3, we just get something that has a completely different value, right? Like having 5 pizzas is a lot different than having like 5/3 of a pizza. So we can never clear fractions if it's not an equation. So an example of this one would be something like 4 over x plus 5 over x plus 2. And again, if there's addition or subtraction, we put it in parentheses. So x and x plus 2 don't have any common factors, right? There's nothing I can multiply one of them by to get the other one. So there's nothing you can multiply x by to get x plus 2 because the operation between the 2 and the x is addition. And so we have to just think of them as two separate factors. And again, that's one of the things that the parentheses do for us is if we put it in parentheses and it can't be factored, then there is no way you can multiply anything else by something to get it. That makes sense, right? Like once we put that x plus 2 in parentheses and it can't be factored, there's nothing I can multiply to get x plus 2 other than 1 and x plus 2. It's prime, like a prime number. So my LCD just has to have a factor of x and it has to have a factor of 2. So we're going to do 4 over x times, I need a factor of x plus 2 here. So notice when we do this, we are multiplying by a factor of 1. So we're multiplying by whatever factors are missing from our denominator on both the top and the bottom, right? Which is different than what we did yesterday when we cleared fractions, because our goal isn't to cancel all of the denominators. Our goal is just to give them all the same factors. And so we are multiplying by whatever factor this one on the left is missing on the top and the bottom, and then same with the right. So plus 5 over x plus 2 times x over x. And so this gives us 4 times x plus 2 plus 5x all over x times x plus 2. And then at this point, we have a single fraction. And so our goal is to factor everything on top and factor everything on the bottom so we can cancel. The bottom is already factored, but the numerator is not because of that addition, right? So 4 times x plus 2 is factored, but the entire numerator isn't factored. So the only way that I have any hope of factoring it would be to combine the whole thing and then break it up again. So we'll distribute. And then combine like terms. So 9x plus 8 over x times x plus 2. And then my numerator has addition, so we'll put it in parentheses. And it can't be factored because there's no exponent and there's no GCF. So then we're just done. Once you put that in parentheses, if you can't factor anything out of it, you can't cancel anything, right? Like you can't cancel part of what's in the parentheses. Either you can factor something out and cancel that, or you're just done. So then what we did yesterday was we solved equations. And it's kind of nice to see these two like side by side because they're somewhat similar, but they have some like important differences. Like we talked about, we can clear fractions in equations, but we cannot clear fractions when we're just adding or subtracting. So even though like the components of the two problems look really similar, the process is different, and it's sometimes easy to like get into this like doing like a hybrid of the two approaches, which kind of just messes up all of it. So our goal here is to get rid of the denominators as opposed to making the denominators the same. So again, we're going to factor only the denominators. But now our goal is to clear fractions. So we want to get rid of denominators. So I'm going to use the same two fractions I did up here. If I have 4 over x equals 5 over x plus 2. Again, I'll put this in parentheses. So now the big difference between these two problems, even though like visually they look pretty similar, is that here I'm adding two expressions and here I'm like actually solving an equation. Right, so the equality says these two things are equal to each other. What's the x value that makes that true? Whereas the addition is just like combine these two values. Like here's 5 jelly beans and 7 jelly beans. Like how many jelly beans are there total? Right. So again, these two processes look really similar visually, but mathematically are very different. So we're going to use the same least common denominator. But we're going to multiply by it over 1. So we have 4 over x. No, how did I do this? There we go. We have x times x plus 2. That's my LCM. But we're putting that over 1 and multiplying it by each term. So equals x times x plus 2 over 1 minus 5 over x plus 2. And what that allows me to do is cancel my denominators. So again, like the big difference that you should see as you're doing this is that after this multiplication bit, notice that in this problem, now my denominators are the same, whereas in this problem, now the only denominators I have are 1s, right? So I've gotten rid of my denominators as opposed to making them the same. And I have to, so here we have to multiply everything by all the factors in the denominator or in the LCM, whereas here we're just multiplying by whatever factors we're missing on both the top and the bottom, so that we can get the same factors. in both denominators. So then this would give me 4 times x plus 2 equals 5x. So 4x plus 8 equals 5x, which gives me x equals 8. And there's the whole bit with like the restricted values and stuff like that, which I left out of this example because I just wanted to focus on like how we're treating the denominators, but that one ends up working because it's not a restricted value. So again, like the main 2 things that we see errors on the test as far as the approach people are taking to the problems is either trying to get common denominators when multiplying or dividing, or trying to clear fractions, like when you're adding or subtracting and you can't clear fractions. So you can only clear fractions in equations. So the idea of this like mixed practice worksheet I'm giving you for homework is just to get you to think really deliberately through like, what do I actually need to factor, and do I need common denominators, or do I clear fractions, right? So like on, whoops, that's the wrong page. Like on this first one, the first thing I would do is look on the right and be like, okay, so this is a multiplication problem, which means I'm going to factor both the numerator and denominator of each fraction, and then I don't get common denominators because it's multiplication, and I don't clear fractions because it's multiplication. And then once I've thought through that whole thing, I can go do what I'm supposed to do. But it just gives you the opportunity to really think through each piece of it before you go and start like throwing factors around in the actual solution. So that'll be your homework for tonight. And now we are going to talk about something completely different. Any questions on just this general sort of wrap up? So far, so good? Okay, so we have to switch gears a little bit. This last section of Chapter 5 is kind of seemingly unrelated to what we've been doing, but it makes use of having to clear fractions and equations and stuff like that, and some factoring, which is, I think, why it's in Chapter 5. So we're doing what's called solving literal equations. Whoops. So this is 5.7. So literal equations are just formulas, basically, and this is one of the areas where one of the skills you'll actually apply to like a lot of different classes. Like we see it all the time in like chemistry and economics and finance, like any area where you have a formula, you often have to solve that formula for one of the variables. So what we're doing is looking at something like, let's say we have like a rectangle and its width is 5, but its length is like variable. So like we can change the length of the rectangle. Well, we know that the area is given by the length times the width. So A equals 5L is a formula for the area of this rectangle. But let's say that instead of wanting to, like, somebody's giving you the length and you want to know what the area is, let's say you have like a certain amount of like, I don't know, like sod or carpet. So you have a known area and you want to figure out how long you can make your rectangle. Well, this is a little bit of a silly example because the calculations are somewhat easy to do that, but it would be more convenient if I had an equation that looked like L equals something, so I could just plug an area in and get L out, instead of having a formula that plugs L in and gives me A out. So all I'm going to do is manipulate this equation to get L by itself, and in this case, I just divide by 5. So we get A equals 5, or A divided by 5 equals L, and we've written another equation that describes the same relationship but has switched like which variable or variables I put into it and which I get out of it. And so that's just the whole idea that we're doing today. It's the process for it is the same as the process for solving any other equation. It just turns out that instead of like having one variable and a bunch of numbers, you have a variable and a bunch of other variables. So we just have to treat all the variables the same way we treat numbers. So let's do a few more examples. Here it is. I left my notes in my other binder, so there's all my examples, because I don't have them in front of me. Let's do this first one. We'll do, actually, I don't like that one. Let's do this one. A equals 3/2 times B minus C. And our goal here is going to be to solve this for B. So first things first, if I see fractions, I want to clear them, and I want that to be the very first thing I do. With these problems, it's especially important because although a lot of these can be solved without clearing fractions, if you don't clear fractions, your solution ends up having complex rational expressions in it, where you have fractions within fractions, and those are not acceptable as like final answers because they're messy and ugly, and nobody wants to work with them. So clearing fractions in the very first step avoids that type of solution. So you always want to clear, if you see fractions, clear them first, like no matter what. So to clear fractions here, I'm going to multiply both sides by 2. So I get 2 times A equals 2 over 1 times 3/2 times B minus C. And notice that like this is all one term. So I can't like multiply it by 2 more than once. It's just like if I'd had 3/2 x on the right side, right? I would just multiply that one term by 3/2. There's no addition or subtraction on that side, and so there's not multiple terms to multiply by 2. So then this guy just cancels the 2. And we end up with 2A equals 3 times B minus C. So now the process for solving for B is exactly the same as it would be if I had something like 20 equals 3 times B minus 5. Right? Like if everything else was a number, I would distribute the 3, right? Like over here, that's the first thing I'd do. So same exact thing here. 2A equals 3B minus 3C. And then we have to get the term that contains B on one side and then the terms that don't contain B on the other side. So this term contains B. These two terms do not contain B. So we're going to use addition or subtraction to get all the ones underlined by red on one side and all the ones underlined by yellow on the other side. So we just get 2A, plus 3C equals 3B. So now if we look at this, all the terms on the left, there's no B's on the left side, and all the terms on the right have B's. Well, there's only one, but. So then how would I solve for B from here? Yeah, just divide by 3, right? So we get 2A plus 3C divided by 3 equals B. And then again, remember that this whole thing is like in parentheses, so we can't like cancel that 3 out unless we can factor it out of the whole entire numerator. I mean, you could also divide term by term, which would end up looking a little bit different, but would still be a perfectly fine answer. But if you divide that whole thing by 3, you cannot do like this thing. That doesn't work because the other term doesn't have a factor of 3. So that would be our final answer.
Could you do like 2/3 A plus C?
Yeah, so like the other thing you could do is divide 2A by 3 and divide 3C by 3, and then you can cancel the 3 because you haven't taken it out of both terms, you just took it out of one of them. And we still have the 2A over 3. So either one of those would be equivalent and totally fine. Okay, let's do another one. is this not working? I lost it. There it is. Oh yeah, let's do the interest formula. So, I'm not going to call it I, I'm going to call it A. Equals P plus PRT. Solve for P. So again, the whole idea, like there's kind of like two pieces of this. The first is to just get all the terms that contain your variable on one side. And when we say your variable, we mean the one you're solving for. And all the terms that don't contain it on the other side. And then we have to get that variable alone. So in this case, if I'm solving for P, this side does not contain any terms with P, and this side only contains terms with P. So we've got that first piece taken care of, where we've got all the terms containing our variable on the right side, and all the terms that don't contain our variable is on the left. But now we have this other problem where like we have two terms that contain P, and the way that we're going to deal with that is just by factoring the P out, because we can see that both terms on the right have a common factor of P. So we can write that as P times 1 plus RT, right? Thinking of this as like 1 times P. Well, now I can get P alone just by dividing, right? So A divided by whatever P is being multiplied by. So these cancel. And we get A over 1 plus RT equals P. So if we want sort of like some tips for like a general approach, we would want to clear fractions, get all terms containing the variable on one side, and all terms not containing the variable on the other side. On the other side, and then we factor out our variable. And divide to isolate it. So in that second bit, when we're getting all the terms that contain the variable on one side and all the terms that don't contain it on the other side, you can only use addition or subtraction here. So you can't divide by anything until you get just that one factor of your variable that you get from factoring it out of one side. So let's do one more example. Which one do I want to do? Let's do, I'm just going to change this one a little bit. Let's do R plus, or no, I'm looking at the wrong one. 5C equals CA over x plus 2 plus 6. So the first thing I want to do here is clear fractions. This is my only denominator, and so I'm going to multiply both sides by x plus 2. So I get 5c times x plus 2 equals x plus 2 over 1 times CA, oh, sorry, we're solving for x. Over x plus 2 plus 6 times x plus 2. So my x plus 2 cancels here. And then, so one of the tricky things about these problems is that you both distribute and you factor. So at this point, we want to distribute. The only thing you will ever factor in these problems is when you factor out the variable you're solving for. If anything is factored other than the variable you're solving for times something else, then you want to distribute. So like on the left side, I see 5c has been factored out. I mean, we didn't actually factor to do it, but 5c is like the GCF on the left side. That doesn't contain the variable I'm solving for, so I have to distribute it. The only factoring you'll ever do will involve the variable you're solving for. So like if you see something like 5cx plus 10c, it's natural to be like, oh, should I factor out a common factor of c here? The answer is no, because c is not the variable you're solving for. So whenever you're tempted to factor out a GCF, ask yourself if that GCF is what you're trying to solve for or not, and if it's not, don't do it. So then over here we get AC. I know I switched the order. The order doesn't really matter, but I always put it in alphabetical order, so that's the only reason I switched it. 6x plus 12. And so now I want all terms that contain my variable, which is x, on one side, and all terms that don't on the other side. So this term contains an x. This term does not contain an x. This term does not contain an x. This term does contain an x. And this term does not contain an x. So I want to get all the terms underlined in yellow on one side and all the terms underlined in red on the other side, and I'm only allowed to use addition and subtraction to do it. So we're going to subtract 6x from both sides. And so now these two terms are the only terms with an x in them, and they're both on the left. So I just have to subtract 10c from both sides to get that 10c on the other side. So we have 5cx minus 6x equals ac plus 12 minus 10c. And now that I've accomplished that, I can factor an x out on the left. And at this point, like, I really don't care at all what's going on the right. As long as there's no x over there, it can be as ugly as we want it to be. All we're going to do is divide it by whatever x is multiplied by over here. So x is equal to this whole thing, whatever it happens to be, over whatever x was multiplied by. So whatever was in those parentheses after I factored. And if you want to put these in parentheses, you can. So one thing to keep in mind as well is that you can't have, like, when you solve for x, you can't have an x on the other side, because then you would have to, like, know what x was to get x, right? Like, so, like, for, where's a good example of it? I guess none of these have this property. Like if you have like 3x equals like 4a minus 5x, you can't just divide both sides by 3, because although that would get x alone on one side, you have this x over here. So if we're thinking about like plugging everything in on the right side so we can spit out a value for x, you would have to know what x was in order to spit out a value for x. Does that make sense? Like you can't solve for x in terms of x because it like defeats the purpose of like inputting a bunch of stuff and getting something out. These are kind of like Excel formulas, right? Like if you imagine like, you know, having a row for something that might change, and then you put an Excel formula, and then you can put different numbers in for one cell and it changes the value of the one you wrote the formula for. So we're thinking of like down here, we could like think of like having all these different values for A and B and C and putting this big formula in, and then I can just plug whatever numbers I want in for A, B, and C, and it's going to like spit out what X is. So if I tried to do that up there, I would also have to know what X was in order to do it, and that would defeat the purpose. So let me give you this so you have a couple minutes to do some of them. These go pretty quick once you get the hang of it.